How you guys doing? Welcome. So today we continue to exploit the most explosive combination of all times, and that is the combination of the fundamental theorem of calculus combined with a little common sense. It's the most explosive combination thus far. So we start off with your daily dose of common sense. Here's your daily dose of common sense. This one comes from your junior high years. Again, if you had a shape like this, could you find the volume? It's a common sense question, and most of you could address it. You'd say, well, you'd first need to find out the radius here. Let's call it r, and then you'd need to find out the height. Let's call this h. That's all you would need. The volume would be equal to pi r squared times h. And there you go. That's your daily dose of common sense. And it shouldn't matter whether this one is this way or that way. You shouldn't need different formulas, whether it's facing up or facing down. It's all common sense. You know, sometimes this height may be a difference of functions, sometimes it may be a difference of y, sometimes it may be a difference of x's. That shouldn't bother you. It's still the same concept. And maybe we could have one more daily dose of common sense. What would happen if you take the same cylinder and made a hole in it with another little baby cylinder? How do you find the volume now? Well, one way to see it would be the big volume minus the little volume. So the big volume would be, you need this r here. The h is still the same for both this inner one and the outer one, and you would need this little. I would call this r the r for the smaller cylinder inside. So the big one would be pi r squared times the height, and the little one would be pi little r squared times the height. So that would be the volume for a cylinder with a hole in it that's shaped like a cylinder, where big R is the big radius and little r is the little radius. Clear? A lot of times people simplify this because they both have a pi and an h. Pi and h, you could factor those out and say, well, this would be pi h times the big R square minus a little r square. That's just a rephrasing of the same idea. That's it. That's your daily dose of common sense. Everything else is brought to you by the fundamental theorem of calculus. So let's get to it. Start off with a simple example. Let's start off with a little modest example here. You take this area bounded by the curves, you know, the x-axis, the curve y equals square root of x, and let's go up to 16 on the x. This is 16, and here we imagine creating a volume out of this by revolving the region around the x-axis. So suppose you spin it around this way, you would create some shape that looks more or less like this. Well, not like that. It would look more or less like this. It would look like this. Every one of these points would be spun around, spun around, spun around, spun around. It would look like more or less like a strawberry. Okay? And the question is, find the volume. The way we're going to find the volume is to slice it up into infinite many little pieces that are infinitely small. So we take the first little piece, we take this little part of the region, and we spin that around. If you spin that around, you would get something that's shaped more or less like this. That's what you would get. That's that little shape spun around. And then you want to ask the fundamental question here. The fundamental question would be, how do you find the volume of that shape? That little volume. Because if you can find that little volume, the differential volume, the fundamental theorem of calculus will help us figure out the sum of all of them. But you don't need much to figure out that volume. All you need is common sense, the kind of stuff that we did at the beginning of the lecture, right, a couple of minutes ago. The volume for that kind of shape would be pi r squared times the height. Let me think. Well, the height is slanted, so that I can already tell you that the height would be this little distance here, which is a different little dx, and the r, well, r would be from here, put my finger on it, to here. That would be the radius, and that is a vertical distance, so it's a difference of y's. That would be this y, which would be the square root of x minus 0. That would be this y. Y is equal to 0 to y is equal to the square root of x. Top minus the bottom. There's top minus the bottom. That's the r squared times the dx. That's, again, the little volume would be pi square root of x squared dx, which would simplify into pi times x times dx. And that comes from just a basic understanding that the volume of a cylinder shape like that is pi r squared times the height. Capiche? And now we do the magical stuff here. We slap an integral on both sides, and we go from I gotta notice that my differential is x, so I gotta look for x limits. I have a whole bunch of these little discs. Let me see if I can show you some of them. Some of the other ones. Let me see. Yeah, I have another one there. I have another one there. I have another one there. I have a whole bunch of these. They're all slightly different sizes. They get smaller as and they get larger as you move to the right because the radius keeps getting larger. But I have many of these, and together they make that strawberry shape, a canonical shape. The question now at the moment is I'm trying to find my limits. X. They go all the way from here all the way down to the smallest ones. Whoa. The smallest ones all the way up to here. So my x's go from 0 to 16. I'm gonna go. My x's go from 0 to 16, and then we're done. We could. That would be a really basic integral. That would be. That would be pi times x squared over 2, and I would go from 16 to 0, giving me pi over 2 times 16 squared minus pi over 2 times 0 squared. And that's it. You're done. Wow, that was amazing, huh? Amazingly simple, thanks to the most explosive combinations of all times. Common sense combined with the fundamental theorem of calculus. It's explosive. It's so nice, I think. That was too easy, right? Want to take it up a notch or two? Alright, so let's do some timeless things here. This one is timeless because, you know, ever since high school, you know that the volume of a cone is equal to 1/3 pi r squared h, right? So if I spin this around the y-axis, I get a cone. The cone would look more or less like this. That's what happens if I spin that region around, which is a cone. And if I wanted to find the volume, I would use this formula, famous formula from high school, 1/3 pi r squared h. But I'm not so much interested in the formula as I am in practicing my slicing skills and my powerful combination of common sense with the fundamental theorem of calculus. So what I want to do is I want to take this and verify this formula, or if I didn't know it, I could prove it. I could use generic numbers here, r for the radius and h for the height, but I just used a specific one that has radius 4 and height 10. But when I'm done with the volume, it should match what we already knew before. Anyways, the secret is you take the cross section, half the cross section, and you spin one little region at a time. When you take a region like this and you spin it around, you would get something like this, right? And the key is to just use common sense to figure out that little volume, and then use the magic of the fundamental theorem of calculus to add them all up, because you got infinite many of these stacked up all the way from the bottom to the top, and they get smaller. Here, I'll draw a couple of these just so you get the idea. There's another one, and this one is smaller. Well, this one, and there's another one, and this one is smaller, even smaller, and you have infinite many of them stacked all the way up. But at this point, I'm just focusing on this one, and I want to find the little volume. The little volume is equal to pi r squared times the height, and in this case that would be r squared. The height, look at the height. The height would be this much. Is that a dx or a dy? Look at it. Of course, that's a little tiny cute dy. Salute. Shaken but not stirred. Don't drink and drive. So now I got to find my r. It's easiest putting your fingers on it. Where's your r? Your radius goes from here to here. It doesn't go from here to here. That's not the radius. Look at the shape. It goes from here to here. Then you think, is that a vertical distance or a horizontal distance? Vertical or horizontal? This would be a horizontal, so therefore it's a difference of x's. And then if you want, you could take baby steps and say, you know what, I'm going to call this one x1 and I'm going to call this one x2. And so the r would be x right minus left. In this case, x2 minus x1. So we continue with our little computation using nothing but common sense. This would be x2 minus x1 squared times your dy. Now it's time to clean that up. x2, you got to use this formula to figure out x2. You could go y minus 10 is equal to negative 10 over 4x. You could multiply both sides by 4. 4y minus 40 is equal to x, and then you could 10x, negative 10x, and then you could divide everything by minus 40 is equal to negative 10x, and you could divide everything by negative 10, so you got negative 4 over 10 y plus 40 over 10 is equal to x. Divide that by negative 10, divide that by negative 10, divide that by negative 10, and there's my x2. That would go right here. What about x1? Well, x1 is 0. That one's easy. And so my little volume would be equal to pi times negative 4 over 10 y plus 4 minus 0. That I'm not going to put that minus 0 squared times dy. Or said differently, my little volume would be pi times negative 2 over 5y plus 4 squared dy. Or I could even clean it up some more. Say this is equal to pi times 4 over 25 y squared minus 8 minus 16 over 5y plus 16 squared times dy. I just did a little foiling there. And now I'm ready for the magic of the fundamental theorem of calculus, and then I observe my limits here, dy. So I need y limits. I need to observe these guys are stacked up starting from down here all the way up to the top. Where does y go from? Y goes from 0 to 10. Again, that's the way I cooked up the example. I wanted a cone that has radius 4 at the bottom but it has height 10. But if it was a more complicated example, you would intersect these two lines, set them equal to each other to give you the y. So I'm going from 0 to 10 in this case, and that would give me, let's see, that would give me pi times 4 over 25 y to the third over 3 minus 16 over 5 y squared over 2 plus 16y. Oh yeah, it's not squared anymore. I already squared it. And I'm going from, this whole thing is times pi, and I'm going from 10 to 0. So that will give me a total of pi times 4 over 25 times 10 to the third over 3 minus 16 over 5 times over 5 times 10 squared over 2 times 16 times 10 minus 0, 0, 0, 0. All that stuff is 0, 0, 0. So I'm not worried about that. And then I just keep cleaning it up. That would give me pi times, let me think, this would be 4 over 3 times, this is 2 times 2 times 2 times 5 times 5 times 5. But I got to cancel those 25, so it just gives me that over the 3. Right? Minus 8. I get 8 over 5. But the 5 cancels with one of those, so it's 10 times 2. Plus 16 times 10. Right? Now how much is that? So these ones cancel. That's 16 times 10 negative, and this 16 times 10 is positive. So that will give me a grand total of pi over just this piece right here. Pi over 3 times 4 times another 4 times 10. Right, this is 4 times 10, which is a grand total of pi over 3 times 4 square times 10. And I write it this way because this should be a familiar way of seeing it. This is how you would have seen it in high school. The volume is 1/3 times pi times a radius squared times a height. Confirming. You could actually prove it. This would be a reasonable way to prove that not that reasonable. It's way too powerful to prove that. But it's a way to show that the volume of a cone is 1/3 pi r squared times a height. Everything would have worked the same way if you replaced the 4 with the generic r for radius and the 10 with the generic h for height. Okay, nice classic example. Alright, let's try this one, but this time let's spin it around a different place. Suppose you spin it around this line right here, which would be the line, let me think, y equals -1. What would happen if you take the entire region and spin it around here? You would get like a strawberry, but with a hole in the middle, because this whole thing, nothing would touch this. It would look more or less like this. Let me see if I could draw it. If you guys have trouble drawing it, what you could do is you always start off with 1 point at a time. Take this point, ignore everything else in the world, just take this point and spin it around. It would look like this. And then take another point, take this point and just spin it around. It would look like this. Take another point, it would spin around. Another point, another point. All you do is take 1 point at a time and you spin it around, and it would look like this, more or less. It would be like a bullet, but with a hole in the middle. Okay? Now, if that's way too difficult, then just spin one little region at a time, one little rectangle. If you spin this little rectangle, you'd get some shape that would look more or less like this. And now the goal would be to find that little volume. If you can find that little volume, then all you really need to find that volume is common sense. But if you can find a little differential volume, then we would use the fundamental theorem of calculus to add up infinite many of these that are stacked right on top, next to each other. So let's do it. So for a volume like that, we talked earlier about it. The volume would be equal to pi r square h minus pi r square h, where you got a big radius. Here's all you got to do is put your fingers on it. Here's the big radius from the axis where you're rotating all the way to the outside cylinder. That's the big radius, and the little radius would be right here. Big radius, little radius. And since these are vertical ones, I can already tell you there's going to be a difference of y's and difference of y's. But I got too many y's here, so I'm gonna start labeling here. I'm gonna call this y1, y2, y3. This is y3. This is y2. This is This is y1. Okay. Y1 is equal to -1, y2 is equal to 0, and y3 is equal to the square root of 3. Or sorry, the square root of x. Alright, so let's get to work now. Finding that little volume. I'm going to need some more room here, so I'm going to erase that, and I'll get to work right now. dV, the little volume, would be equal to pi, the big R. Put your fingers on it. Where's the big R? Big R is right here. Vertical or horizontal? That would be a vertical distance, so it's y3 minus y1 squared times a height. How big is this little, what's the height for that little cylinder? It's this tall. So that would be a dx minus pi times, let me see, the little r. That would be vertical distance, so it's a difference of y's. y2 minus y1 squared times the height, again, would be dx. Right? And then you would continue to work on this and try to clean it up as much as you can. y3 is equal to the square root of x minus y1 is equal to 0 square dx. Sorry, y1 is not 0. y1 is -1, so that would be a +1. Nice. Minus pi times y2, which would be equal to 0, minus y1, which is -1, so that makes it a +1 squared times a dx. Again, you got to make sure you're doing this carefully. y1, that's this one, y1 is -1, so when you subtract the y1 it's +1, which makes sense. Whatever this radius was, you add 1 to it, and that would be your big radius. Where the little one is always 1. That for all of these ones, the little radius is 1. Alright, so we continue plowing right through this. This would be pi, I gotta do a little FOIL here, x minus 2 square roots of x plus 1 dx, minus 1 squared is 1, so that's just pi dx. And I continue with this. Little volume would be, I can factor out the pi and the dx. That would leave a x minus 2 square root of x plus 1, and then minus 1 dx, because if you have a plus 1 and a minus 1 there, I factor out the pi and I factor out the dx, that leaves a minus 1. For a grand total of little volume, which would be pi times x minus 2 square root of x times dx. Nice. Most explosive combination of the entire class, the combination of common sense and the fundamental theorem of calculus. If you can imagine it, anything you can imagine slicing up into infinite many little pieces, you can do it. If you can imagine it, the fundamental theorem of calculus will add it for you. Isn't that a nice thing? I think I've made my point on that. How many things have we sliced up? We've sliced up work, we've sliced up moments, we've sliced up torques, we've sliced up little arcs. Everything that you can slice up, we've sliced up little washers. They call these washers. Anything that you can slice up into infinite little pieces, you can add. Salute to that. I drink to that. Alright, so the little fundamental theorem of calculus. Observe the index here, or the differential dx, and the x limits. So we said we're going from 0 to 16. So we'll go from 0 to 16. And really the rest of that is kind of boring, so I won't do it. But it's a nice little problem. Slicing up, getting washers out of these. Okay? You could do so many things with the original region. You could spin around this one, you could spin around some other axis over here, you could spin around some axis over here, you could spin around the y-axis all day long, and the problems would be almost identical. You would just have to put your fingers on the radius and figure out what that is and put it in here. And you could solve all of these more or less the same way. Let's do one more. So suppose you take this curve here, y equals x squared, and suppose you spin around this line, say x equals I don't know, x equals 3. If you do that, you might want to just spin one little region at a time. So spin that one, and then calculate that little volume, and then add them all up. Let's see. A little volume for that kind of shape would be the pi times a big R squared times a height minus pi times a little r squared times a height. That's not using anything fancy, that's just using common sense. So let's look at the big R. Put your fingers on it. Where's the big radius? It goes from here to here? No. From here to here? No. From here to here? No. From here to here? Yes. That's the big radius. Horizontal or vertical distance? This is a horizontal distance, so therefore it's a difference of x's. I got too many x's here. I'm going to call this x1, I'm going to call this x2, I'm going to call this x3, because I got too many x's going on here. So put your fingers on the big radius is this one right here. So there's always right minus left, so I'm going to go with x1 minus x3. Bish. Times the height. Oh, the height is easy. This is the height right here. Little dy. Minus pi times the little r squared times the height, which will again be a dy. Little r. Put your fingers on it. All you need to do is put your fingers on it. Whoops. Take it easy. Right here. This is the little radius. So that would be right minus left. That would be x1 minus x2. That's the little radius. And as easy as that sounds, that's all you got to do. This would be pi x1, let me think. Oh, I got to figure these out. x1 we said was equal to 3. Oh, that's easy. 3 minus x3. Oh my goodness, x3. I got to solve for x. x3 would be equal to, I'll solve for it. x3 is equal to the square root of y. So that's what my x is equal to. I plug that into here. Square root of y, and I gotta square that, and then a dy minus pi times x1. That was equal to 3 minus x2. x2 was equal to 1 square times dy. And I continue fearlessly simplifying this guy. Give me 9 minus 6 square roots of y plus y dy minus 2 squared 4 pi dy. Right? And altogether that would give me, I got a 9 pi dy's and 4 pi dy with a negative. That would give me a total of 5. 5 pi's minus 6 pi's square root of y plus pi y. That's when I distribute this, add them all together. All this times dy. That's what it looks like when you clean it up. Nothing fancy, it's just algebra. And the most explosive combination. Anything you can imagine slicing up in infinite many pieces, the fundamental theorem of calculus can add it for you with great elegance. I observe my y limits. Where am I going from? Y goes from, let's see, I got a whole bunch of these stacked up. They're going from here all the way to here. So the y limit, let me think, the y limit would go from here, y is equal to 0 to here, whatever this point is. To find that point, that's this point, you would intersect this one with this one. X equals 1 with y equals x squared. That's these two lines, and that would give you that y is equal to 1. So, therefore, y is going from 0 to 1. And the rest of that is pretty boring. So, yeah, these are super easy to integrate. I'll do it. I'll do one more step of it. That's it. 5 times pi times y minus 6 times pi times y to the 3/2 divided by 3/2 plus pi times y squared over 2, as that goes from 1 to 0. Plug in 1 in there, you get 5 pi minus 6 pi divided by 3/2 plus pi over 2 minus 0. There you go. See why they pay me? Pretty easy, right? You can do everything. As long as you have a little common sense and you've got the fundamental theorem of calculus by your side, nothing can harm you.